Tonight we are going to talk about a star. Not our star, not the sun. Something else entirely. Something so large that the human mind genuinely cannot process it. No matter how many analogies we stack up, no matter how many comparisons we draw. You will hear the numbers tonight, and you will understand them intellectually, but some part of your brain will quietly refuse to believe them. That is normal. These numbers were not designed for brains like ours. The star we are going to talk about sits roughly 19,000 light years from where you are right now. You cannot see it. Not with your eyes, not with binoculars, not even with a modest backyard telescope. It is buried behind thick lanes of interstellar dust near the center of our galaxy, hidden in a region so dense with stars and gas and debris that visible light from this part of the sky barely reaches us at all. Astronomers can only observe it in infrared, a kind of light our eyes were never built to detect. Its name is Stephenson 218. It is, as of the best measurements we currently have, the largest star ever discovered, and by the end of tonight, you are going to understand what that actually means. Not just the size, not just how it compares to our Sun, or to Jupiter, or to the orbit of Saturn. You are going to understand why this star disturbs the people who study it, why its existence sits uncomfortably at the edge of what physics says should be possible, and why when it finally dies it may not even have the courtesy to explode. But we are going to get there slowly, because the only way to truly grasp the scale of the largest star ever found is to start with the star you already know. Let us begin with the Sun. The Sun is, by any human standard, enormous. Its diameter stretches roughly 865,000 miles across. If you could somehow hollow it out, you could pour about 1.3 million Earths inside and still have room left over. It accounts for 99.86% of all the mass in our entire solar system. When you add up every planet, every moon orbiting those planets, every asteroid tumbling through the asteroid belt, every comet drifting in the outer reaches, every grain of dust and every frozen chunk of ice in the Kuiper belt, all of it combined makes up less than 0.2%. The Sun is, for all practical purposes, the solar system. Everything else is debris caught in its gravity. The Sun is powered by nuclear fusion. Deep in its core, where temperatures reach roughly 15 million degrees Celsius and the pressure is about 250 billion times the atmospheric pressure on Earth's surface, hydrogen atoms are being crushed together so violently that they fuse into helium. Every single second, the Sun converts approximately 600 million tons of hydrogen into roughly 596 million tons of helium. The missing 4 million tons do not disappear. They are converted directly into energy, following Einstein's famous equation. 4 million tons of mass turned into pure energy every second of every day for the last 4.6 billion years. That energy works its way outward from the core through a dense radiative zone where photons bounce and scatter for tens of thousands of years before finally reaching the convective zone, where rising columns of hot plasma carry the energy to the surface. When the energy finally escapes as light, it crosses the 93 million miles between the Sun and Earth in about 8 minutes and 20 seconds. This means that when you look at the Sun, you are not seeing it as it is right now. You are seeing it as it was 8 minutes ago. If the Sun vanished this instant, you would not know for over 8 minutes. The Earth would continue orbiting empty space, still bathed in the last light, to leave before the Sun disappeared. The surface of the Sun, called the photosphere, has a temperature of about 5,500 degrees Celsius. That is hot enough to vaporize virtually every known material. Tungsten, the metal used in old incandescent light bulb filaments because of its extraordinarily high melting point, would melt and then boil away on the Sun's surface. Diamond would not survive. Steel would not survive. Nothing you have ever touched or held or built would survive. And yet, 5,500 degrees is considered moderate in the world of stars. There are stars whose surfaces burn at 30,000 degrees, 40,000 degrees. Some of the hottest stars known exceed 200,000 degrees Celsius. at their surfaces. The Sun is not a hot star. It is not a particularly large star. It is not an unusually bright star. On the grand scale of stellar astronomy, the Sun is almost aggressively ordinary. Astronomers classify stars using a system based on their surface temperature and colour. The hottest stars burn blue or blue-white and are classified as O-type and B-type stars. These are rare, massive, and short-lived. Slightly cooler stars burn white or yellow-white and include A-type and F-type stars. The Sun falls into the G-type category, a yellow dwarf sitting comfortably in the middle of the temperature range. Below the Sun are K-type stars, which are orange, and M-type stars, which are red and are the coolest and most common stars in the galaxy. The Sun has been burning for about 4.6 billion years. It has enough hydrogen fuel remaining to continue for roughly another 5 billion years. That sounds like an almost incomprehensible amount of time, and it is. But on the scale of stellar lifetimes, it is perfectly average. The Sun is a middle-aged star living a quiet, stable life in a relatively calm neighbourhood of the galaxy. Our solar system sits roughly 26,000 light-years from the centre of the Milky Way, in a region called the Orion Spur, which is a minor arm branching off from the larger Sagittarius arm of our spiral galaxy. We are not in the dense, chaotic core where stars are packed tightly together and radiation levels would make life impossible. We are not on the sparse outer edge where stars thin out and the galaxy fades into intergalactic space. We are in between, in a stable zone where conditions have been calm enough for life to develop over billions of years without interruption. The Sun orbits the centre of the galaxy at roughly 500,000 miles per hour. That is fast by any human standard. It is fast enough to travel from New York to Los Angeles in about 18 seconds. But at galactic scales, it is glacially slow. One complete orbit takes approximately 225 million years. Since the Earth formed 4.6 billion years ago, we have completed only about 20 laps around the galaxy. Dinosaurs appeared less than one galactic orbit ago. All of human civilization, from the first stone tools to this moment, has occurred in less than 1/10,000th of a single galactic year. I bring all of this up not because it is directly about the largest star ever found, but because you need to feel the Sun's scale before you can understand what it means when I tell you the Sun is small. Not small compared to Earth, obviously. Not small compared to anything you have ever seen or touched. But small compared to what we are heading toward. If you place the Sun next to some of the stars we are about to discuss, you would not be able to see it. Not because it would be dim, but because it would be physically too tiny. Like a marble next to a house. Like a grain of sand next to a beach ball. Like a single red blood cell next to a basketball. The Sun is our reference point. It is the unit of measurement astronomers use when they talk about stellar sizes. They call it 1 solar radius. When they say a star has a radius of 10 solar radii, they mean its radius is 10 times the Sun's. When they say 100 solar radii, they mean the star stretches from its centre to its surface, a distance 100 times farther than the Sun does. The star we're heading toward tonight has a radius of approximately 2,150 solar radii. That number will mean more to you later. For now, just hold it in your mind. 2,150 suns stacked edge to edge, from the centre of this star to its surface. We will get there, but first we need to climb. The nearest star to our Sun is Proxima Centauri, a small red dwarf sitting about 4.24 light-years away. That is roughly 25 trillion miles. If you could drive there at highway speed, the trip would take about 43 million years. Even light, travelling at the fastest speed anything can move in this universe, takes over 4 years to cross the gap, and Proxima Centauri is our closest neighbour. Most stars are much, much farther away. Proxima Centauri is tiny by stellar standards. Its radius is roughly 14% of the Sun's. If the Sun were the size of a basketball, Proxima Centauri would be about the size of a tennis ball. But what it lacks in size, it makes up for in longevity. Red dwarfs burn their fuel so slowly that they can live for trillions of years. Long after our sun has swollen into a red giant, shed its outer layers, and collapsed into a white dwarf, Proxima Centauri will still be quietly burning, barely changed. Now let us start climbing. Sirius is the brightest star in Earth's night sky. It sits about 8.6 light-years away in the constellation Canis Major, the Great Dog. Sirius is a binary system, meaning it is actually two stars orbiting each other. The main component, Sirius A, is a white main-sequence star, roughly 1.7 times the radius of our Sun. So a bit larger, a bit hotter, and considerably more luminous. About 25 times brighter than the Sun. But in terms of physical size, Sirius A would not look dramatically different if placed next to our Sun. You could tell them apart, but you would recognize them as being in the same general category. Move up the ladder. Pollux is an orange giant star about 34 light-years away, the brightest star in the constellation Gemini. Its radius is roughly 9 times that of the Sun. If Pollux replaced the Sun at the center of our solar system, its surface would extend about halfway to Mercury's orbit. It is a noticeably large star, but we are still in the range of what feels intuitively reasonable. 9 times the Sun. Big but comprehensible. Climb higher. Arcturus is a red giant star about 37 light-years from Earth, the brightest star in the northern celestial hemisphere. Its radius is approximately 25 times that of the Sun, 25 solar radii. If Arcturus sat where the Sun is, its surface would extend well past the orbit of Mercury and approach the orbit of Venus. Mercury would not exist. It would be inside the star. Venus would feel the heat of a stellar surface less than 20 million miles away. Arcturus is part of a class of stars called red giants, stars that have exhausted the hydrogen in their cores and begun fusing helium. Their outer layers have expanded and cooled, giving them their characteristic orange-red colour. The Sun will become a red giant in about 5 billion years. When it does, its radius will expand to roughly 100 to 250 times its current size, eventually engulfing Mercury and Venus, and possibly reaching the orbit of Earth. But Arcturus is not even close to the top of our ladder. Keep climbing. Aldebaran, the eye of the constellation Taurus the Bull, has a radius roughly 44 times that of the Sun. It is an orange giant, about 65 light-years away. Its surface, if centered on the Sun's position, would extend past Mercury and reach about halfway to the orbit of Earth. Rigel, the blue supergiant anchoring the foot of Orion, is a different kind of giant entirely. Where Aldebaran and Arcturus are cool, old and red, Rigel burns blue-white hot with a surface temperature of roughly 12,000 degrees Celsius, more than twice the Sun's. Its radius is about 79 times the Sun's. Rigel is massive, roughly 21 times the mass of the Sun, and it is extraordinarily luminous, shining with about 120,000 times the Sun's brightness. It sits roughly 860 light-years away, and despite that enormous distance, it is one of the brightest stars in our sky. Rigel is a young star, only about 8 million years old, but it is burning through its fuel at such a ferocious rate that it will not live much longer. Within the next few million years, Rigel will likely explode as a supernova. Now we arrive at the stars that begin to strain comprehension. Betelgeuse. You may have heard this name. It is the red supergiant marking the left shoulder of Orion, one of the most recognizable stars in the night sky. If you have ever looked up at Orion during a winter evening and noticed that one of its corner stars glows distinctly red while the others burn white or blue, you are looking at Betelgeuse. Betelgeuse has a radius of approximately 887 times that of the Sun. Some estimates place it slightly higher, around 900 to 1000 solar radii, depending on the measurement technique and the wavelength of light used to observe it. Betelgeuse does not have a firm, well-defined surface. Its outer atmosphere is incredibly diffuse, almost ghost-like, trailing off gradually into space. The boundary between the star and not the star is blurry, which is why different measurements give different sizes. But even taking the lower estimates, Betelgeuse is staggering. If you placed Betelgeuse where the Sun is, its surface would extend past the orbit of Mars. Mercury, Venus, Earth, and Mars would all be inside the star. The asteroid belt would graze the outer layers of its atmosphere. Jupiter would be the closest surviving planet, orbiting just outside the surface of a star so large that light takes over 2 hours to cross its diameter. For comparison, light crosses the Sun's diameter in about 4.6 seconds. It crosses Betelgeuse's diameter in roughly 2.5 hours. Betelgeuse is roughly 700 light-years from Earth. It is only about 8 to 8.5 million years old, which is young by stellar standards. The Sun is 4.6 billion years old and is considered middle-aged. Betelgeuse has lived less than 0.2% of the Sun's current age, and it is already dying. Massive stars live fast and die young. The more massive the star, the faster it burns through its fuel and the shorter its life. A star with 10 times the mass of the Sun might live only 20 million years. A star with 20 times the Sun's mass might live less than 10 million years. The most massive stars known burn through their entire hydrogen supply in just a few million years, a cosmic blink. Betelgeuse has exhausted the hydrogen in its core. It is now fusing heavier elements, helium into carbon and oxygen, in concentric shells surrounding an increasingly dense core. Its outer envelope has expanded enormously as a result, ballooning outward to its current immense size. The star is unstable. It pulsates, brightening and dimming over irregular periods. In late 2019, Betelgeuse underwent a dramatic and unexpected dimming episode that briefly made global news. For a few months, the star faded to roughly 1/3 of its normal brightness, dimmer than it had been in recorded observational history. Some speculated it was about to explode. It was not. Later analysis revealed that the dimming was caused by a massive cloud of dust expelled from the star's surface, temporarily blocking the light reaching Earth. Betelgeuse will eventually explode as a supernova. When it does, it will briefly outshine every star in the galaxy, becoming visible in the daytime sky on Earth. The explosion will be spectacular but harmless at 700 light-years distance. The supernova might happen tomorrow. It might happen in 100,000 years. We have no way of knowing precisely when. Antares, the heart of the constellation Scorpius, is another red supergiant roughly comparable to Betelgeuse. Its radius is estimated at about 680 to 800 solar radii. It sits roughly 550 light-years away, shining with a distinctly red-orange hue that makes it one of the most visually striking stars in the summer sky. These are large stars, genuinely enormous by any reasonable definition, but they are not even in the top tier of the largest stars known. Betelgeuse, with its 887 solar radii, would barely register as a mid-sized contender on the list we are about to explore. The stars we are heading toward now do not merely dwarf the Sun, they dwarf Betelgeuse the same way Betelgeuse dwarfs the Sun. To understand why these extreme stars exist at all, you need to understand a bit about what happens when a massive star begins to die. A star on the main sequence, the long stable phase where it fuses hydrogen into helium, maintains itself through a constant balancing act. Gravity pulls the star's mass inward, trying to crush it. The energy released by fusion pushes outward, creating pressure that resists the crush. These two forces exist in an equilibrium called hydrostatic equilibrium. The star neither collapses nor explodes. It just burns steadily for millions or billions of years. But when the hydrogen in the core runs out, this equilibrium is disrupted. The core, now made of helium ash, contracts under gravity because there is no longer enough energy being produced at the center to push back. As the core contracts, it heats up. This increased temperature ignites hydrogen fusion in a shell surrounding the inert core. The energy output from this shell burning is enormous, far greater than what the core was producing before. This flood of energy from the shell pushes the outer layers of the star outward. The star expands. As it expands, the surface cools because the same amount of energy is now spread over a much larger area. The surface temperature drops from the sun like 5,500 degrees down to 3,000 or 4,000 degrees. The star turns red. It has become a red giant, or for the most massive stars, a red supergiant. The more massive the original star, the more extreme this expansion. Stars that were 10 times the mass of the sun might expand to a few hundred solar radii. Stars that were 20 to 30 times the mass of the sun can expand to 1,000 solar radii or more, and the outer layers of these expanded stars become almost unimaginably diffuse. Near the surface of a red supergiant, the gas is thinner than the best vacuum we can create in a laboratory on Earth. If you could somehow stand on the surface of Betelgeuse, which has no solid surface to stand on, but humour the thought experiment, you would see a dim red glow stretching to the horizon in every direction, and the gas around you would be so thin that for all practical purposes, you would be standing in space. It would not feel like being inside a star. It would feel like being nowhere. This is the process that creates the largest stars in the universe. Not growth in the way we normally think of it. Not a star getting more massive or consuming more material. It is inflation. A dying star's outer layers being pushed outward by the desperate energy of shell burning as the core contracts and heats up. The star is not thriving, it is in its death throes, and those death throes cause it to swell to sizes that seem genuinely impossible. Let us now meet the stars that push this process to its absolute limit. The first contender most people encounter when they search for the biggest star is VY Canis Majoris. For a long time, it was the star that held the popular imagination. VY Canis Majoris sits roughly 3,900 light-years from Earth in the constellation Canis Major, the same constellation that hosts Sirius, the brightest star in our sky. But where Sirius is a modest, well-behaved main sequence star, VY Canis Majoris is something else entirely. It is a red hypergiant, a classification reserved for the most extreme, most unstable, most luminous red supergiants known. Its radius is estimated at roughly 420 times that of the Sun. If VY Canis Majoris replaced the Sun at the centre of our solar system, its surface would extend well past the orbit of Jupiter. Mars, the asteroid belt, Jupiter, all would be inside this star. Saturn would orbit just outside the surface, bathed in the faint red glow of a stellar atmosphere so vast that light takes nearly 6 hours to travel around its circumference. VY Canis Majoris is roughly 270,000 times more luminous than the Sun. It has about 17 times the Sun's mass, which might not sound like much for a star this large, but that is because most of its mass has been, and continues to be, blown away. This star is hemorrhaging material at a rate that defies easy description. Every year, VY Canis Majoris loses roughly 30 times the mass of the entire Earth in stellar wind, great gusts of gas and dust being pushed off the surface by radiation pressure. Over its lifetime, it may have already shed half of its original mass. Observations from NASA's Hubble Space Telescope have revealed that the material being ejected from VY Canis Majoris is not leaving smoothly or evenly. The star is throwing off enormous arcs and knots of material in random directions, at different speeds, at different times. These ejections look something like the coronal mass ejections our Sun produces, but scaled up by orders of magnitude. Some of these arcs extend thousands of times farther from VY Canis Majoris than the Earth is from the Sun. They form a complex asymmetric nebula surrounding the star, a cloud of expelled gas and dust that makes it extremely difficult to determine the star's precise properties. Roberta Humphreys, an astrophysicist at the University of Minnesota who has studied VY Canis Majoris extensively, has described it as one of the most remarkable stars known. Her team's research, published in the Astronomical Journal in 2021, showed that the mass loss events on VY Canis Majoris are far more complex than standard models predicted. The star appears to have enormous convection cells on its surface, each one potentially as large as the entire Sun or larger, and these cells periodically erupt, launching material into space. Here is the first unsettling detail about VY Canis Majoris. When a star this massive dies, the standard expectation is a supernova, a spectacular explosion that briefly outshines an entire galaxy. But VY Canis Majoris may not cooperate. Humphreys and her colleagues have suggested that rather than exploding, VY Canis Majoris might simply collapse directly into a black hole without any explosion at all. The star might have already shed so much mass through its violent eruptions that when the core finally gives out, the remaining material simply falls inward. For an observer watching from a safe distance, the star would appear to gradually dim over a period of months or years, and then it would be gone. No flash, no supernova remnant, no expanding nebula lit from within by radioactive decay. Just a star that was there and then was not. We will return to this idea later. For now, hold on to it. The next name you will often see in discussions of the larger stars is UY Scuti. For several years, UY Scuti was widely cited as the largest star known, the reigning champion, the star that YouTube videos and popular science articles pointed to when they wanted to demonstrate the mind-bending scale of the cosmos. UY Scuti was first catalogued in 1860 by German astronomers working at the Bonn Observatory as part of a comprehensive survey of the sky. They noticed that the star's brightness changed over time, pulsating with a period of roughly 740 days, and designated it as a variable star. It sits in the constellation Scutum, near the centre of the Milky Way, roughly in the same region of sky as many of the other extreme stars we will discuss tonight. In 2012, a team of astronomers used amber interferometry at the Very Large Telescope in Chile to measure UY Scuti's size directly. They found an angular diameter on the sky, compared it to the assumed distance of about 9,500 light-years, and calculated a radius of approximately 1,708 solar radii, plus or minus 192. This made it, at the time, the largest star directly measured, 1,708 solar radii. If UY Scuti replaced the Sun, its surface would extend past the orbit of Jupiter, possibly reaching the orbit of Saturn. The volume of UY Scuti, based on this measurement, would be roughly 5 billion times the volume of the Sun. You could pour 5 billion suns inside this star. The number was extraordinary, and it captured public attention. UY Scuti became the go-to answer for the question, what is the biggest star in the universe? But then something happened that illustrates one of the central difficulties of this entire field. The European Space Agency's Gaia spacecraft, launched in 2013, spent years measuring the precise positions and distances of over 1 billion stars in the Milky Way. When Gaia's data releases began to arrive, they included a distance estimate for UY Scuti that was significantly different from the one used in the 2012 calculation. Instead of 9,500 light-years, the Gaia data suggested UY Scuti might be only about 5,900 light-years away, much closer than previously thought. This matters enormously. When astronomers calculate a star's physical size, they start with its apparent size on the sky, its angular diameter, and then multiply by the distance to get the actual size. If the distance is wrong, the calculated size is wrong. If UY Scuti is 5,900 light-years away instead of 9,500, then its radius is not 1,708 solar radii. It drops to roughly 755 solar radii, about the same size as Antares. Still enormous, still a red supergiant, but no longer the record holder, not even close. The Gaia measurements come with their own caveats. Red supergiants are notoriously difficult for Gaia to measure accurately because their surfaces are not point-like. They have extended pulsating atmospheres and surrounding dust shells that can confuse the spacecraft's sensors. The astrometric noise in UI-Scuti's Gaia data is very high, meaning the measurement might not be reliable. A 2021 reanalysis using improved methods placed UI-Scuti at about 5,900 light-years, supporting the shorter distance, but the uncertainty remains. So here is the situation. UI-Scuti might have a radius of 1,708 solar radii, making it one of the largest stars ever measured. Or it might have a radius of 755, making it a fairly ordinary red supergiant. The difference comes down to a distance measurement that we cannot pin down with confidence. And this is not an unusual situation. This is the norm for extreme stars. Let us move to another contender. WOHG 64 is a red supergiant located not in our galaxy, but in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, roughly 163,000 light-years from Earth. Because it is in a separate galaxy, at a known distance, some of the distance uncertainty that plagues Milky Way stars is reduced, though not eliminated. WOHG 64 was discovered in the 1970s and has long been estimated to have a radius of roughly 1,540 solar radii, surrounded by a thick torus of dust that makes it one of the most dust-enshrouded stars known. For decades, it appeared to be a straightforward, if extreme, red supergiant. Then in 2024, a team of astronomers led by Gonzalo Muñoz Sanchez at the National Observatory of Athens noticed something unexpected. The star's colour was changing. Its surface temperature appeared to be increasing. They concluded that WOHG 64 was transitioning from a red supergiant into a yellow hypergiant, a much smaller and hotter type of star. If this interpretation was correct, the star's radius had contracted dramatically, down to roughly 800 solar radii. But in January 2026, new spectroscopic data from Jaco van Loon's team at Kiel University challenged this conclusion. The data showed molecular absorption bands that are characteristic of a cool red supergiant, not a yellow hypergiant. WOHG 64 might still be a red supergiant after all. The debate continues. A single star, 163,000 light-years away, and astronomers cannot agree on what colour it is. Whether it is a red supergiant or a yellow hypergiant, whether its radius is 1,540 or 800 solar radii. This is not a failure of astronomy. This is the reality of trying to measure objects so distant and so extreme that our best instruments are operating at their absolute limits. There is also RSG C1-F01, a red supergiant in the star cluster RSG C1 within our own Milky Way, in the constellation Scutum. Its radius has been estimated at between 1,436 and 1,530 solar radii, measured by Roberta Humphreys and her team in 2006 using infrared surveys. The cluster itself was only discovered in 2006 and can only be observed in infrared because optical telescopes cannot see it through the dust. This star sits among a handful of objects that approach what theory suggests is the upper limit for stellar radius in our galaxy. And then there is Stephenson 2-18, Stephenson 2-18, also known as ST 2-18, also catalogued as Stephenson 2DFK1 and RSGC 2-18, is a red supergiant located in the constellation Scutum, approximately 19,000 light-years from Earth, near the open cluster Stephenson 2. The cluster was first noticed by American astronomer Charles Bruce Stephenson in 1990 in data from a deep infrared survey. Stephenson identified a group of faint, dust-reddened stars, several of them probable red supergiants, clustered together in a small area of sky. The brightest star in the region was given the identifier 1 in the first analysis of the cluster, but it was considered an outlier. It did not quite match the rest of the cluster members in position or proper motion, and its brightness was abnormally high. Later studies gave the same star the number 18 in a different catalogue system, and the designation Stephenson 2-18 became widely used. In 2012, a study using the Australia Telescope Compact Array and a radiative transfer model called DUSTY calculated the star's properties. Based on an assumed distance of about 5.5 to 5.8 kiloparsecs, roughly 18,000 to 19,000 light-years, and an effective surface temperature of about 3,200 Kelvin, they estimated a luminosity of roughly 440,000 times the Sun's. From the temperature and luminosity, they derived a radius, 2,150 solar radii. Let that number sit for a moment. 2,150 times the radius of the Sun. The Sun's radius is roughly 696,000 kilometers, or about 432,000 miles. Multiply that by 2,150 and you get a radius of approximately 1.5 billion kilometers, a diameter of roughly 3 billion kilometers. If Stephenson 2-18 replaced the Sun at the center of our solar system, its surface would extend past the orbit of Saturn. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, all would be inside this star. Only Uranus and Neptune would remain outside, orbiting in a vastly altered system dominated by a star so large that it would cover most of the sky from their perspective. Light, travelling at 186,000 miles per second, would take almost 9 hours to complete a single trip around the star's circumference. For comparison, light circles the Sun in about 14.5 seconds. Light circles the Earth in about 0.13 seconds. The volume of Stephenson 2-18 is estimated at roughly 10 billion times the volume of the Sun. You could fit 10 billion suns inside. If you started counting to 10 billion right now, one number per second, without stopping to eat, sleep, or breathe, you would finish in about 317 years. This is the largest star we have ever found. But here is where the story takes its disturbing turn. Stephenson 2-18 should not be as large as it is, not according to the physics we use to model every other star in the universe. There is a concept in stellar astrophysics called the Hayashi limit, named after the Japanese astrophysicist Chushiro Hayashi, who described it in 1961. The Hayashi limit is a theoretical boundary on how large and how cool a star can be, while still remaining in hydrostatic equilibrium, the balance between gravity pulling inward and pressure pushing outward that keeps a star from either collapsing or flying apart. The mathematics behind the Hayashi limit are grounded in thermodynamics and the physics of energy transport inside stars. In simple terms, as a star expands and its surface cools, at some point it becomes fully convective, meaning energy is transported from the core to the surface entirely by the physical movement of hot gas rising and cool gas sinking, rather than by radiation passing through the stellar material. This is the same process you see in a pot of boiling water. Hot water rises from the bottom, cooler water at the surface sinks back down. When a star reaches this fully convective state, it sits on what astronomers call the Hayashi track in the Hertzsprung-Russell diagram, which is the master chart relating a star's temperature to its luminosity. The Hayashi limit forms a nearly vertical line on this diagram at temperatures around 2,500 to 4,000 Kelvin. Stars cannot exist in a stable state to the right of this line, at cooler temperatures or larger radii, because they would be unstable. Their outer layers would not be able to maintain equilibrium. The radiation pressure from within would overwhelm gravity's ability to hold the outer layers in place, and the star would begin to shed mass uncontrollably. For red supergiants, the theoretical upper limit on radius is estimated to be roughly 1,500 solar radii. Stars can approach this limit, and some may briefly exceed it during periods of instability, but a star sitting comfortably at a radius well above 1,500 solar radii for an extended period is difficult to reconcile with current stellar evolution models. Stephenson 218's estimated radius of 2,150 solar radii exceeds this theoretical limit by more than 40%. This creates a genuine puzzle. Either the measurement is wrong, which is entirely possible and perhaps likely, or the theory is incomplete, which is also possible, or something is happening in this particular star that we do not understand. Let us examine the measurement problem first because it is the most probable explanation, and understanding it reveals something important about the limits of what we know. Measuring the size of a star 19,000 light-years away is not like measuring the size of an object on Earth. You cannot wrap a tape measure around it. You cannot even directly resolve it as a disk in most telescopes. At 19,000 light-years, even a star 2,150 times the size of the Sun is an unresolvably tiny point of light. What astronomers measure is the star's angular diameter, the fraction of a degree it subtends on the sky, using techniques like interferometry, where multiple telescopes are combined to achieve resolution far beyond what any single telescope could manage. But angular diameter alone tells you nothing about physical size. To convert an angular diameter into an actual radius, you need to know the distance. And the distance to Stephenson 2-18 is not well established. The star's distance is usually derived from its assumed membership in or proximity to the open cluster Stephenson 2, which has a kinematic distance of roughly 5.8 kiloparsecs, about 19,000 light-years. This distance was calculated by measuring the cluster's radial velocity, how fast it is moving toward or away from us, and comparing that to models of how the Milky Way rotates. But Stephenson 2-18 may not actually be a member of the cluster. Its position on the sky is slightly offset from the cluster core. Its proper motion does not perfectly match the other cluster members, and its brightness is abnormally high compared to the other red supergiants in the cluster. If Stephenson 2-18 is not at the same distance as the cluster, if it is a foreground star significantly closer to us, then its calculated luminosity and radius would drop substantially. A distance error of just 30% would bring the radius estimate down from 2,150 solar radii to something closer to 1,500, which would place it right at the theoretical limit rather than dramatically above it. The uncertainty in the distance has been estimated at greater than 50% in some studies, which means the true distance could range from roughly 12,000 to 25,000 light-years. The radius estimate swings wildly across that range. Beyond the distance problem, there is the fundamental difficulty of defining where a red supergiant ends and space begins. These stars do not have surfaces in any conventional sense. There is no sharp boundary, no edge you could point to and say this is where the star stops. Instead, the density of the stellar atmosphere decreases gradually as you move outward from the core. Near the centre, the gas is incredibly dense and hot. At the photosphere, the region that defines the nominal surface, the gas is already extremely thin, and beyond the photosphere, there's a vast extended atmosphere of even thinner gas, dust, and molecular material that can stretch for hundreds of additional solar radii. When astronomers measure the size of a red supergiant, they typically measure the Roslin radius, which is the distance from the centre to the point where the optical depth reaches a specific value, roughly the point where the star becomes opaque to most light. But this boundary changes depending on what wavelength you observe in. In visible light, the star might appear to have one size. In infrared, where the cooler outer layers emit more strongly, the star appears larger. In radio wavelengths, where you can detect molecular masses in the extended atmosphere, the star might appear larger still. Stephenson 2-18's radius of 2,150 solar radii was derived from its luminosity and effective temperature using the Stefan Boltzmann law, which relates a star's luminosity to its temperature and surface area. If you know how luminous a star is and you know its surface temperature, you can calculate its radius. But the luminosity depends on the distance, which is uncertain, and the temperature depends on the spectral analysis, which can be complicated by the star's circumstellar dust shell and extended atmosphere. Small errors in either quantity propagate into large errors in the radius. The star's spectral type is classified as M6, which corresponds to a surface temperature of about 3,200 Kelvin. This is unusually cool, even for a red supergiant. Most red supergiants have spectral types between M0 and M4, with temperatures between 3,500 and 4,000 Kelvin. An M6 classification places Stephenson 2-18 below what is sometimes called the Hayashi limit for its luminosity class, in a temperature regime where stellar models predict the star should be unstable. And yet there it is, or at least there its light is, travelling toward us from a point 19,000 light-years away, carrying information about a star that our models say should not be that large, at a distance we are not confident about, with a temperature cooler than theory says it should have, surrounded by a dust shell that makes it difficult to measure anything precisely. This is the first disturbing truth about the biggest star ever discovered. We are not confident in the number. The measurement is built on assumptions layered on top of assumptions, each one carrying its own uncertainty. The star might be 2,150 solar radii. It might be 1,500. It might be something in between. We do not know, and with current technology, we cannot resolve the question definitively. But the uncertainty itself is part of what makes this story significant. These extreme stars exist at the very limits of what we can observe and what we can model. They are the test cases for our understanding of stellar physics. Every time we find a star that appears to break the rules, we either learn that our measurements were wrong, which teaches us about the limitations of our instruments, or we learn that our physics was incomplete, which teaches us something new about how the universe works. Either outcome advances our understanding. But in the meantime, we sit with the discomfort of not knowing. There is a second layer to this discomfort, and it goes beyond the measurement problem. Even if Stephenson 2-18's radius is closer to 1,500 solar radii than to 2,150, that still places it right at the theoretical limit. And it is not alone. There are several other stars that hover near or above this boundary. WOHG 64, RSG C1-F01, NML Cygni, MY Cephei, all have estimated radii that approach or exceed 1,500 solar radii. The existence of multiple stars near this limit suggests that either the limit is slightly higher than currently calculated, or these stars are passing through a brief, unstable phase where they temporarily exceed the limit before shedding enough mass to drop back below it. The latter possibility is supported by the extraordinary mass loss rates observed in these stars. VY Canis Majoris, as we discussed, loses roughly 30 Earth masses per year. Stephenson 2-18 has an estimated mass loss rate of about 1.35 thousandths of a solar mass per year, which is among the highest known for any red supergiant. These stars are actively tearing themselves apart. Their radiation pressure is pushing material off their surfaces faster than gravity can hold it in place. They exist in a state of constant erosion, shedding layers of their outer atmosphere into space, slowly whittling themselves down. It is possible that these stars periodically swell past the Hayashi limit during episodes of intense mass loss, then contract slightly as the mass loss reduces their luminosity and radiation pressure, then swell again. A kind of stellar breathing, each breath sending another pulse of material into the interstellar medium. If this is the case, then the extreme radii we measure are snapshots of stars caught at their maximum expansion, moments of instability that do not last long in astronomical terms. But even this interpretation raises questions. If these stars are unstable, if they are oscillating near the theoretical limit, then we need to understand what drives those oscillations. Standard stellar evolution models do not predict this kind of behavior for red supergiants. The models predict a relatively smooth expansion to a maximum radius, followed by the end of the star's life. They do not predict repeated episodes of extreme swelling and contraction. Something is happening inside these stars, or on their surfaces, or in the interaction between their radiation fields and their extended atmospheres, that our models are not capturing. And there is a deeper question still. The Hayashi limit is calculated using assumptions about how energy is transported inside fully convective stars. Those calculations rely on a parameter called the mixing length, which describes how far a rising bubble of hot gas travels before it dissipates its heat into the surrounding material. The mixing length is not derived from first principles. It is a free parameter that is calibrated against observations. For most stars, the calibration works well, but for the most extreme red supergiants, we have very few data points to calibrate against. We are extrapolating from a theory that was developed for smaller, better understood stars. If the mixing length behaves differently at the extreme end of the stellar mass and luminosity range, then the Hayashi limit itself might be different from what we calculate. Three-dimensional radiation hydrodynamic simulations of convection in red supergiants are extraordinarily computationally expensive. In these stars, the convection cells can be as large as half the star itself. The entire stellar surface might contain only a handful of convective cells at any given time, each one rising and falling over periods of years. This is nothing like the convection in the Sun, where millions of small granulation cells cover the surface, each one lasting only minutes. Simulating the full three-dimensional convection in a red supergiant from first principles remains at the edge of what modern supercomputers can handle. So we are left with a situation where our best theory says, these stars should not be this large, but our best observations suggest some of them are. The measurements are uncertain, the theory is approximate, and both are operating at the limits of their capabilities. This is the landscape of extreme stellar astrophysics. It is not a landscape of confident answers. It is a landscape of careful uncertainties, where the honest answer to how big is the biggest star is probably somewhere between 1,500 and 2,150 times the size of the Sun. We're not sure. And figuring out exactly where in that range it falls might require fundamentally new observations or fundamentally revised theory, possibly both. But before we move on to the question of how these stars die, let us sit with the scale a bit longer, because the numbers deserve more than a passing acknowledgement. Before we leave the question of size, let us spend a few more moments with these numbers, because the human brain has a way of hearing a large number, nodding politely, and then moving on without actually processing what it means. When I say Stephenson 2-18 has a radius of 2,150 solar radii, that sounds impressive, but it does not land in the body the way it should. So let us try to make it land. Think about an airplane, a commercial airliner, the kind you might take on a transatlantic flight, cruises at roughly 575 miles per hour. If you boarded a plane and flew in a straight line around the equator of the Sun, the trip would take about 190 days, a little over 6 months. That is a long flight, but it is at least conceivable. You could bring enough books. Now try the same trip around Stephenson 2-18. At the same speed, 575 miles per hour, the flight would take roughly 139 years. You would board the plane in the year 2026 and arrive back at your starting point in approximately the year 3165. The Roman Empire would have been a recent memory when you departed, By the time you landed, human civilization would have undergone over a millennium of change. Entire nations would have risen and fallen. Languages would have evolved beyond recognition, and you would have spent every moment of those 1,139 years flying at cruising speed around the surface of a single star. Or consider light. Light is the fastest thing in the universe, travelling at roughly 186,000 miles per second. At that speed, it takes light about 4.6 seconds to cross the diameter of our Sun. It takes light about 9 hours to complete a single trip around the circumference of Stephenson, 218. 9 hours. If you turned on a flashlight and somehow directed the beam around the star's surface, you could go to sleep, wake up, eat breakfast, and the light would still be making its way around. Here is another way to think about it. Light takes about 1.3 seconds to travel from the Earth to the Moon. It takes about 8 minutes and 20 seconds to travel from the Sun to Earth. It takes about 4.2 hours to travel from the Sun to Neptune, the outermost planet. From the centre of Stephenson 2-18 to its surface, light takes roughly 1.4 hours. The star's radius, measured in light travel time, is comparable to the distance from the Sun to Saturn. The interior of this star is a volume of space that light needs hours to traverse. Now imagine you're on a spacecraft approaching Stephenson 218 from interstellar space. You have been travelling for centuries or millennia, crossing thousands of light years, and now you are within a few light years of the star. What would you see? At first, from several light years away, you would see a bright red point of light against the background stars. Not dramatically different from many other red stars in the sky from that vantage point. Red supergiants are luminous, roughly 440,000 times the luminosity of the Sun in the case of Stephenson 2-18. So you would notice it, but it would still appear as a point, as all stars do from such distances. As you drew closer, within a fraction of a light year, you would begin to notice something unusual. The star would start to appear not as a point, but as a disk. Stars are so far away that even through telescopes, almost all of them appear as unresolved points of light. But Stephenson 2-18 is so physically large that at relatively close range, it would subtend a noticeable angle on the sky, a visible disk of dim red light, and surrounding that disk you would see a vast, complex nebula of gas and dust. The circumstellar envelope, the material blown off the star's surface by radiation pressure and stellar winds, extends far beyond the star itself. This envelope contains dust grains made of silicates and other minerals, molecular gas including water, silicon monoxide, and hydroxyl molecules, all of which can be detected by their Massa emissions. Intense focused beams of microwave radiation produced when molecules in the envelope are energized by the star's radiation. The nebula would not be smooth or uniform. It would be clumpy, asymmetric, with arcs and knots and streamers of denser material, punctuated by voids where the gas has been swept away. Some of the arcs might span distances comparable to the diameter of our solar system. Others might be smaller, denser, more recently ejected. The overall impression would be of a star that is disintegrating in slow motion, peeling itself apart layer by layer, casting its material into the darkness. As you drew closer still, approaching the outer boundary of the star's diffuse atmosphere, you would enter a region where the distinction between star and space becomes meaningless. There is no hard edge. The density of gas just increases gradually as you move inward. A few atoms per cubic centimetre at the outermost fringes, then a few dozen, then hundreds, then thousands. The gas glows faintly red from the star's thermal radiation, but at first the glow would be dimmer than the faintest twilight on Earth. You would still see background stars through the haze. Moving deeper, the glow would intensify. The temperature would rise slowly from the cold of interstellar space toward the 3,200 Kelvin of the photosphere. The background stars would begin to disappear behind the thickening haze of gas and dust. The sky would gradually shift from black to a deep red as the thermal radiation of the surrounding gas became the dominant source of light, and the star would fill more and more of your field of view. Not the way a building fills your view as you drive toward it, growing from a small shape on the horizon to a structure overhead. This would be different. The star's surface, such as it is, curves away from you in every direction. At a certain distance, the surface would seem almost flat, the way the Earth's surface seems flat when you stand on it, because the curvature is so gentle that your eyes cannot perceive it. You would be standing on the surface of a world so large that its geometry is indistinguishable from a plane. The surface itself would not look like what you might expect from the surface of a star. It would not be a smooth, glowing sphere. It would be roiling, turbulent, covered in enormous convection cells where hot gas rises from the interior and cooler gas sinks back down. Each of these cells might be tens of millions of miles across, larger than the orbit of Mercury. From close range, you would see these cells as bright, slowly shifting regions of slightly hotter gas surrounded by darker boundaries where cooler gas descends. The overall pattern would shift and change over months and years, the surface constantly reshaping itself as convection carries energy upward from the interior. Occasionally, one of these convection cells might erupt, a massive upwelling of hot gas breaking through the surface, launching material into the circumstellar envelope. This would be the stellar equivalent of a solar prominence, but scaled up by a factor of 1,000. Arcs of glowing gas rising hundreds of millions of miles above the surface, curving outward, some of the material falling back, some of it escaping entirely, carrying heat and momentum and enriched material into space. And beneath all of this, buried under 1.5 billion kilometers of diffuse gas, the core, small, dense, furiously hot, burning through its remaining nuclear fuel at an accelerating rate, the engine that powers the entire vast structure, the dense heart of a dying star. You would never reach the core. No spacecraft could survive the journey inward. The temperatures increase rapidly as you descend. The pressures increase. The radiation intensifies. Long before you reach the depth where nuclear reactions are occurring, the heat and pressure would destroy any material we know how to build with. But you could study the core from outside by analysing the neutrinos it produces, by measuring the oscillations of the surface that reveal the internal structure, by observing the chemical composition of the ejected material that tells you what reactions are happening deep inside. This is, in fact, exactly what astronomers do. They cannot visit these stars. They cannot even resolve most of them as anything more than points of light. But they can detect the signatures of what is happening inside by carefully analysing the light, the infrared radiation, the radio emissions, the molecular mass lines, the chemical abundances in the circumstellar material. They can reconstruct the internal structure of a star 19,000 light-years away from the faint signals it sends toward us, encoded in photons and neutrinos and gravitational ripples in the fabric of space. Now let us talk about what surrounds Stephenson 218 in its neighbourhood, because the context matters. Stephenson 218 sits near a massive open cluster called Stephenson 2, one of the most massive open clusters known in the Milky Way. Open clusters are groups of stars that formed from the same molecular cloud at roughly the same time. They are gravitationally bound, meaning the stars orbit around a common centre of mass, but only loosely. Over time, gravitational interactions with the rest of the galaxy gradually strip stars from open clusters, dispersing them into the general galactic population. Most open clusters dissolve within a few 100 million years. Stephenson 2 is notable because it contains an unusually high number of red supergiants, at least 26 confirmed members, making it one of the richest collections of extreme evolved stars known. These stars are all roughly the same age, born from the same cloud of gas, and they have all reached the red supergiant phase at roughly the same time, which tells us The cluster is probably between 14 and 20 million years old, the right age for stars of 12 to 16 solar masses to have evolved off the main sequence and begun their terminal expansion. The presence of so many red supergiants in one cluster is a gift for astronomers. It provides a population of extreme stars at roughly the same distance, allowing comparisons of their properties to be made more reliably than if each star were at a different, poorly known distance. It is like having a laboratory filled with specimens of the same type, each one showing a slightly different phase of the same evolutionary process. Whether Stephenson 2-18 is actually a member of this cluster remains debated. Its position on the sky is slightly offset from the cluster core. Its brightness is abnormally high compared to the other members. Its proper motion, the slow drift across the sky caused by its physical motion through the galaxy, does not perfectly match the cluster. Some studies classify it as a cluster member. Others classify it as a foreground or background object at a different distance, which would mean its calculated luminosity and radius are wrong. This ambiguity matters because it directly affects the star's estimated size. If it is a cluster member at 19,000 light-years, the radius estimate of 2,150 solar radii stands. If it is a foreground object at, say, 12,000 light-years, the radius drops to something closer to 1,400 solar radii, still enormous but below the theoretical Hayashi limit and no longer record-breaking. Resolving this question will likely require future observations, possibly from next-generation infrared interferometers or from improved astrometric data as the Gaia spacecraft continues to refine its measurements of stellar positions and distances across the galaxy. Until then, the uncertainty remains. And there is something honest about admitting that science is not a collection of final answers. It is a process of refining questions, narrowing uncertainties, getting closer to the truth without ever claiming to have arrived at it absolutely. The question of how big the biggest star is remains open. The best current answer is probably somewhere between 1,500 and 2,150 solar radii, and we are not sure exactly where in that range it falls. That range itself tells a story. Even the lower end, 1,500 solar radii, represents an object so far beyond everyday experience that it might as well be infinite from a human perspective. The difference between 1,500 and 2,150 solar radii, while significant for stellar physics and for resolving the Hayashi limit question, does not change the fundamental takeaway for someone trying to grasp the scale of the universe. Either way, this star is incomprehensibly large. Either way, it is dying. Either way, it will leave behind material that the galaxy will recycle into new stars and planets for billions of years to come. The precision matters for physics. The awe is the same either way. Let us now consider the other giant stars that round out the top of the list, because they each have their own stories and their own disturbing qualities. NML Cygni is a red supergiant in the constellation Cygnus, roughly 5,300 light-years from Earth. Its radius has been estimated at between 1,642 and as high as 2,775 solar radii, though the upper end of that range is considered unreliable. It is one of the most luminous stars in the Milky Way, shining with approximately 270,000 times the luminosity of the Sun. Like VY Canis Majoris, it is surrounded by a complex circumstellar envelope and is losing mass at an extraordinary rate. NML Cygni is a strong matter source, emitting intense microwave radiation from water and silicon monoxide molecules in its envelope. These MESA emissions can be used to trace the dynamics of the mass loss, revealing how material is being ejected from the star's surface and how it interacts with the surrounding interstellar medium. Mie Tephai, also known as Herschel's garnet star because of its deep red colour, is another red supergiant with an estimated radius between 1,134 and 2,061 solar radii. The enormous range in that estimate reflects the uncertainty in the star's distance and the difficulty of measuring its angular diameter through its thick circumstellar envelope. Mai Tefei sits in the constellation Cepheus, roughly 5,000 to 15,000 light-years away, depending on which distance estimate you use. Westerlund 126 is a red supergiant or possible red hypergiant in the massive star cluster Westerlund 1, one of the most massive young star clusters known in the Milky Way. Its radius has been estimated at roughly 1,530 to 2,544 solar radii, again with significant uncertainty. Westerlund 1-26 is notable because it sits in a cluster that contains an extraordinary diversity of extreme stars, including blue hypergiants, yellow hypergiants, Wolf-Rayet stars, and a magnetar, a neutron star with an incredibly powerful magnetic field. The cluster is like a zoo of the most exotic stellar types known, all in one place. Each of these stars shares the same characteristics that make Stephenson 218 so difficult to measure and so interesting to study. They are all red supergiants in the final stages of their lives. They are all losing mass at extraordinary rates. They are all surrounded by thick circumstellar envelopes of dust and gas. They are all at poorly determined distances, and they all have radius estimates that are either near or above the theoretical Hayashi limit. Together, they form a population of extreme stars that collectively challenge our understanding of the upper limits of stellar size. One or two outliers could be dismissed as measurement errors, but a consistent population of stars clustering near the theoretical limit, with some appearing to exceed it, suggests that something more systematic is going on. Either the limit is slightly higher than currently calculated, or these stars are in a transient phase of instability that allows temporary excursions beyond the limit, or there are physical processes at work in the most extreme red supergiants that our current models do not account for. This is an active area of research. New observations are being made, new models are being developed, and slowly the picture is becoming clearer. But tonight the picture is still incomplete, and that incompleteness is, in its own way, the most fascinating part of the story. We are looking at stars that sit at the boundary of what physics allows, measured by instruments that are operating at the limits of what technology can achieve, and we are finding that the universe is more complex, more uncertain, and more surprising than our models predicted. There is one more important distinction that we should explore before we close tonight, because it is a source of frequent confusion and it reveals something important about what these giant stars actually are. When most people hear that Stephenson 218 is the largest star ever discovered, they naturally assume it must also be one of the most massive stars. Larger means heavier, right? In everyday life, a bigger object usually contains more material. A large rock weighs more than a small rock. A bigger dog has more mass than a smaller dog. Our intuition tells us that size and mass go together. In stellar physics, this intuition is completely wrong. The largest stars in the universe are not the most massive, and the most massive stars in the universe are not the largest. These are two entirely different superlatives, and the record holders in each category are very different kinds of objects. Stephenson 2-18, with its estimated radius of 2,150 solar radii, has a mass of probably somewhere between 20 and 40 solar masses. That is heavy, certainly, far heavier than the Sun, but it is nowhere near the most massive star known. The most massive star currently known is R1361, located in the Tarantula Nebula in the Large Magellanic Cloud, roughly 163,000 light-years from Earth. R1361 has an estimated current mass somewhere between 196 and 315 times the mass of the Sun, depending on which study and methodology you use. making it the heaviest star ever measured. But its radius is only about 35 to 43 solar radii. It is a compact, blindingly luminous Wolf-Rayet star, blue-white and ferociously hot, with a surface temperature exceeding 46,000 Kelvin. It is roughly 5 to 7 million times more luminous than the Sun. If you placed it where the Sun is, it would appear as a blinding blue-white point in the sky, its surface far inside the orbit of Mercury, radiating enough ultraviolet light to sterilize every planet in the solar system many times over. R136 A1 contains 5 to 10 times more mass than Stephenson 2-18, packed into a volume that is millions of times smaller. It is dense, hot and compact. Stephenson 2-18 is diffuse, cool and vast. They represent opposite extremes of what stars can be. The reason the most massive stars are not the largest is straightforward. Massive hot stars produce enormous radiation pressure from their cores, but that radiation is produced in a relatively small volume and pushes against a dense, tightly bound envelope. The star stays compact because the gravity from its enormous mass keeps the outer layers firmly in place. These stars are so hot that their surfaces glow blue-white, and their energy is radiated efficiently from a relatively small surface area. Red supergiants like Stephenson 2-18 are large precisely because their outer layers are weakly bound. The core is small and dense, but the envelope has expanded so far from the core that gravity's grip is tenuous. The gas at the surface is so thin, so spread out, that the star's enormous physical size translates to a surprisingly modest total mass. Most of the volume of a red supergiant is essentially empty space, with a faint scattering of atoms in it. If you could somehow weigh Stephenson 2-18, you would find that despite being 10 billion times the volume of the Sun, it is probably only 20 to 40 times the Sun's mass. This means its average density is fantastically low. If you divided the star's total mass by its total volume, you would get a density lower than the best vacuum we can create in any laboratory on Earth. The average density of Stephenson 2-18 is probably less than a millionth of a gram per cubic centimetre. For comparison, the average density of air at sea level on Earth is about 1.2 grams per cubic centimetre. The air you're breathing right now is over 1 million times denser than the average density of the largest star ever found. You could fly through most of Stephenson 2-18 and not even notice you were inside a star. Your spacecraft would register a faint red glow in all directions and a slight warming of its outer hull, but the gas surrounding you would be so thin that for all practical purposes, you would be in a vacuum. Only as you approach the inner regions, closer to the core, would the density and temperature increase to the point where you would recognize that you are inside a stellar structure. This is the paradox of the largest stars. They are the biggest objects in the stellar category, but they are also, in a sense, the emptiest. Most of their volume is a near vacuum. The actual dense, massive material, the core where nuclear reactions occur, the shells of fusing elements surrounding the core, all of this occupies a tiny fraction of the star's total volume. The rest is atmosphere, diffuse, extended, barely held in place by gravity, slowly drifting away into space. It is as if someone inflated a balloon to the size of a city, but used only a single breath of air to do it. The balloon is enormous, but the material inside is negligible. Pop it, and almost nothing comes out. That is essentially what a red supergiant is. A small, dense core surrounded by an impossibly vast bubble of almost nothing. This is also why the concept of a surface is so problematic for these stars. Where does the balloon end? For a normal balloon, the answer is obvious. The rubber membrane defines the boundary. But for a red supergiant, there is no membrane. There is just a gradual transition from slightly denser gas to slightly less dense gas, fading by imperceptible degrees into the interstellar medium. The surface we assign to the star is an arbitrary line drawn at a specific optical depth. a convention rather than a physical reality. When we say Stephenson 2-18 has a radius of 2,150 solar radii, what we really mean is that at a distance of 2,150 solar radii from the centre, the gas is dense enough to be opaque to most wavelengths of light. Beyond that distance, you can see through the gas. Below it, you cannot. That is the photosphere, and it is the conventional surface. But material extends well beyond it. In the chromosphere, the extended atmosphere, and the circumstellar envelope, reaching distances that may be several times the photospheric radius. So in a very real sense, Stephenson 2-18 is even larger than its quoted radius. The star, including its extended atmosphere and its circumstellar envelope, occupies a volume of space that stretches far beyond the 2,150 solar radii. How far beyond depends on where you decide the star ends, and that decision is, to some extent, arbitrary. This fuzziness, this refusal to have a clean boundary, is one of the qualities that makes these stars so frustrating and so fascinating to study. They do not fit neatly into categories. They do not yield clean measurements. They resist the precision that science thrives on, offering instead a range of possible values, a cloud of uncertainty, an answer that is always approximately rather than exactly. And perhaps that is the most honest way to end our exploration tonight. Not with a definitive statement, not with a clean number, but with an acknowledgement that the universe is under no obligation to be simple. The biggest star ever discovered is approximately 2,150 times the radius of the Sun. Approximately. That word carries more meaning than all the numbers combined. It means we have measured something almost immeasurably distant and almost immeasurably large. And we have gotten close to the truth, but we have not reached it. Not yet. Maybe not ever. Not completely. But closer than we were before. And that is what matters. The star burns. The photons travel. The measurements improve. The models are refined. And slowly, generation by generation of astronomers working with generation after generation of instruments, we get a little closer to understanding what it is we are looking at when we turn our telescopes toward the dusty centre of the Milky Way and detect the infrared glow of a star that has no business being as large as it is. That process, that slow convergence on truth, is one of the most beautiful things humanity has ever undertaken. It does not make headlines. It does not produce dramatic revelations. It produces decimal places. It produces error bars that shrink by fractions of a percent. It produces papers that update the radius estimate from 2,150 plus or minus 300 to 2,150 plus or minus 250. Small steps, almost invisible progress, but over decades and centuries, those small steps accumulate. The picture sharpens, the uncertainties narrow, and eventually, what was once a blur becomes a portrait. Not perfect, not complete, but recognizable. A star, impossibly large, beautifully unstable, burning quietly in the dark, waiting for its physics to play out to their conclusion. That is Stephenson 2-18. That is the biggest star we know. A sphere of almost nothing, anchored by a small, dense, dying core, stretched to proportions that physics says should be impossible, measured by instruments that can barely resolve it, defined by a surface that does not really exist. And now, let us talk about how it ends. Every star that has ever existed, every star that currently burns in the sky tonight, and every star that will ever form in the future, will die. There are no exceptions. The universe does not allow permanent structures. Given enough time, everything falls apart. Stars are no different. How a star dies depends almost entirely on how massive it was when it was born. Low-mass stars like our Sun will die quietly. In about 5 billion years, the Sun will exhaust its core hydrogen, swell into a red giant, shed its outer layers into space as a beautiful glowing shell called a planetary nebula, and leave behind a small dense core called a white dwarf. The white dwarf will be roughly the size of Earth but contain about half the Sun's mass. It will glow faintly from residual heat, slowly cooling over trillions of years, eventually becoming a cold, dark cinder drifting through space. No explosion, no violence, just a slow fade into darkness. Stars more massive than about 8 to 10 times the mass of the Sun do not get this gentle exit. They die in supernovae. The process begins the same way it does for smaller stars. The core exhausts its hydrogen. The star expands into a red supergiant. But the core of a massive star is much hotter and denser than the core of a star like the Sun. It is hot enough and dense enough to fuse heavier elements. After the hydrogen is gone, the core contracts and heats up until it can fuse helium into carbon and oxygen. When the helium is exhausted, the core contracts again and begins fusing carbon into neon and magnesium, then neon into oxygen and magnesium, then oxygen into silicon and sulfur, then silicon into iron. Each successive fuel burns faster than the last. A massive star might burn hydrogen for millions of years. It burns helium for roughly 1 million years. It burns carbon for about 1,000 years. It burns neon for approximately 1 year. It burns oxygen for months. It burns silicon into iron in approximately 1 day. In the final hours of a massive star's life, the core is a frantic cascade of nuclear reactions, burning through each fuel in a fraction of the time it took to burn the previous one. The star develops an onion-like structure with concentric shells of different elements surrounding the core. An outer shell of hydrogen, beneath it a shell of helium, then carbon, then neon, then oxygen, then silicon, and at the very centre an inert core of iron. Iron is the end of the line. Every nuclear reaction that has powered the star up to this point has released energy. Fusing hydrogen into helium releases energy. Fusing helium into carbon releases energy. All the way up the periodic table, each fusion reaction has produced slightly less energy than the one before, but it has always been net positive. Iron is different. Fusing iron does not release energy. It requires energy. It is an energy sink, not an energy source. When the core becomes iron, fusion stops. And when fusion stops, the outward pressure that has been supporting the star against gravity vanishes. The core is suddenly unsupported. What happens next takes less than a second. The iron core, which is roughly the size of Earth but contains about 1.4 times the mass of the Sun, collapses under its own gravity. It collapses at roughly a quarter the speed of light. In less than a second, the core shrinks from the size of Earth to a sphere about 12 miles across. The density in this collapsed core reaches about 400 trillion grams per cubic centimetre. A teaspoon of this material would weigh about 1 billion tons. Protons and electrons are forced together to form neutrons. The core becomes a neutron star, the densest stable form of matter known in the universe. The collapse happens so fast that the outer layers of the star do not have time to react. They begin falling inward, chasing the collapsing core. But when the core reaches neutron star density, it becomes incompressible. It cannot be squeezed any further. The infalling material slams into this incompressible core and bounces. A shock wave forms and begins racing outward through the star. At the same time, the collapsing core releases an enormous flood of neutrinos. These ghostly particles, which barely interact with matter under normal conditions, are produced in such incredible numbers during the collapse that even their feeble interactions are enough to deposit vast amounts of energy in the material just above the core. This neutrino energy revives the stalled shockwave and drives it outward through the rest of the star. The shockwave rips through the star's outer layers at speeds of 10,000 to 30,000 kilometers per second, tearing the star apart. The outer layers are blasted into space, forming an expanding cloud of gas and debris called a supernova remnant. For a few weeks, the dying star outshines its entire galaxy, producing as much light as 10 billion suns. Then it fades, leaving behind either a neutron star or, if the original star was massive enough, a black hole, surrounded by the expanding remnants of what used to be a star. This is the standard story, the core collapse supernova. Type 2. It is one of the most violent events in the universe, and for most massive stars, it is the expected ending. But there are alternatives, and for the most extreme stars, the alternatives may be more likely than the standard path. The first alternative is a hypernova. A hypernova is an exceptionally energetic supernova, releasing roughly 10 times more energy than a standard core collapse event. Hypernovae are thought to occur when the collapsing core of a very massive star, typically one born with more than 30 times the mass of the Sun, forms a rapidly spinning black hole rather than a neutron star. The rotation drives twin jets of material outward from the poles of the black hole at nearly the speed of light. These jets plough through the remaining stellar material, creating powerful shock waves that produce an explosion far more luminous than an ordinary supernova. Hypernovae are associated with long-duration gamma-ray bursts, brief but incredibly intense flashes of gamma radiation that can be detected from billions of light-years away. A gamma-ray burst from a hypernova can release more energy in a few seconds than the Sun will produce in its entire 10 billion-year lifetime. These are among the most energetic events observed in the universe, second only to the Big Bang itself. VY Canis Majoris, with its extreme mass and luminosity, is thought to be large enough to potentially produce a hypernova when it dies. If it does, the explosion would release more energy than 100 standard supernova. The gamma-ray burst, if pointed in Earth's direction, which is statistically very unlikely, could theoretically sterilize worlds thousands of light-years away by stripping away their atmospheres and bombarding their surfaces with lethal radiation. The second alternative is far stranger. It is called a failed supernova, or more accurately, a direct collapse. The idea is straightforward in principle, but deeply unsettling in implication. For some very massive stars, particularly those in the higher mass ranges with complex internal structures, the standard supernova mechanism may simply fail. The core collapses as expected. The shockwave forms as expected. But the shockwave does not have enough energy to break through the dense material above the core. It stalls, and instead of blasting the outer layers into space, the shockwave falls back. The material that was supposed to be ejected falls inward instead, joining the collapsing core. The entire star collapses into a black hole. Not just the core, but most or all of the stellar material. For an observer watching from a distance, the star does not explode. There is no brilliant flash, no expanding supernova remnant, no weeks of outshining a galaxy. Instead, the star brightens slightly, perhaps for a few months as the outer layers begin to shift and the initial stages of collapse release some energy. Then the star fades, and then it is gone, replaced by a black hole that emits nothing. This is not just theory, it has been observed. In 2009, astronomers monitoring individual stars in nearby galaxies noticed that a red supergiant in the spiral galaxy NGC 6946, roughly 22 million light-years away, had begun to brighten slightly. The star, designated N6946-BH1, had approximately 25 times the mass of the Sun. It was a large, evolved red supergiant, exactly the kind of star that should have eventually exploded as a supernova. For a few months, N6946-BH1 grew slightly brighter, reaching a luminosity roughly 1 million times that of the Sun. Then it faded. By 2015, when astronomers looked at the star's position using the Hubble Space Telescope, the star was gone. It had vanished from visible light and near-infrared images. A small amount of infrared light was still detected at the star's former position, likely coming from debris falling onto a newly formed black hole. But the star itself, a massive red supergiant that should have produced one of the most spectacular explosions in the universe, had simply winked out of existence. Christopher Kochenek and his team at Ohio State University, who had been deliberately searching for exactly this kind of event, published their findings in the monthly notices of the Royal Astronomical Society. They had been monitoring approximately 1 million red supergiants across multiple nearby galaxies, comparing images from different years, looking for stars that disappeared without producing supernova. N6946-BH1 was the first, and so far the only, clear example they found. Based on this single detection, combined with the overall rate of supernova in the observed galaxies, Kochenek estimated that as many as 30% of massive stars might end their lives this way, silently collapsing into black holes without any supernova at all. 30%. Nearly 1 in 3 massive stars disappearing without a trace. This number is still preliminary. It is based on a single confirmed event and a statistical extrapolation. Future observations may revise it significantly, but the fact that this mechanism exists at all, that a star can simply collapse into nothingness without any outward explosion, is one of the most quietly disturbing findings in modern astrophysics. The theoretical explanation for why this happens involves the details of how different stars burn carbon in their cores during the final stages of life. In lower mass red supergiants, roughly 10 to 17 solar masses, carbon burning occurs convectively, meaning the material in the core is constantly being mixed and stirred. This convective burning produces a core structure that allows the supernova shockwave to punch through the overlying material relatively easily. In higher mass red supergiants, above roughly 17 to 20 solar masses, carbon does not burn convectively. This leads to a more extended core with denser material surrounding it. When the core collapses, the shockwave has to push through this denser layer. If the layer is thick enough, the shockwave stalls and fails. The explosion never happens. The star collapses. The dividing line between explosion and collapse is not sharp. It depends on the star's mass, its rotation rate, its metallicity, the details of its internal structure, and possibly other factors we have not yet identified. There may be stars below 17 solar masses that collapse silently, and stars above 20 solar masses that explode spectacularly. The physics is complex and still being worked out. What does this mean for Stephenson 218? We do not know Stephenson 218's mass with any precision. Estimates for red supergiants of its luminosity suggest an initial mass of roughly 20 to 40 solar masses, but the star has been shedding mass at an extraordinary rate for its entire red supergiant phase, so its current mass could be significantly lower. If its current mass is below the threshold for a failed supernova, it might still explode conventionally. If it is above the threshold, it might collapse silently, or it might produce a hypernova if the conditions are right. If the core collapses into a rapidly spinning black hole, if jets form, if those jets are energetic enough to break through the remaining stellar material. We genuinely do not know which fate awaits the largest star we have ever found. It could produce the most spectacular explosion visible from Earth, bright enough to see in the daytime sky, despite being 19,000 light-years away. Or it could simply vanish. One of the largest structures in the known universe, quietly folding into a black hole, leaving behind nothing but a gravitational memory and a slowly dispersing cloud of dust. Both possibilities are real. Both are supported by current theory, and we will not know which one occurs until it happens, which could be thousands of years from now, or could have already happened. The light from the event still travelling toward us across 19,000 light-years of interstellar space. There is something deeply unsettling about this uncertainty. We have built an extraordinarily detailed understanding of stellar physics. We can model the internal structure of stars with remarkable precision. We can predict how long a main sequence star will burn, what elements it will produce, when it will expand into a giant, and roughly when it will die. And yet, for the largest and most extreme stars, the ones that push the boundaries of what physics allows, we cannot say with confidence whether they will end in a bang or in silence. The universe does not guarantee a dramatic ending just because the beginning was spectacular. Let us now consider what these stars leave behind, regardless of how they die. Let us go deeper into the life that led to this moment. Because to truly understand why Stephenson 2-18 exists in the form it does today, you need to understand the journey that brought it here. Not just the broad strokes we covered earlier, but the specific physical transformation that turns a newborn star into a bloated, dying giant. Stephenson 2-18 was born roughly 10 to 20 million years ago. We do not know the exact date because stellar ages are estimated from evolutionary models rather than directly measured, and the models depend on assumptions about the star's initial mass, rotation rate, and chemical composition, all of which carry uncertainties. But the age range is consistent with a star that was born with approximately 20 to 40 times the mass of the Sun in a dense, turbulent molecular cloud somewhere in the Scutum Centaurus arm of the Milky Way. When it was born, Stephenson 2-18 would have looked nothing like it does today. It would have been a hot, blue, intensely luminous O-type or early B-type star. Its surface temperature would have been somewhere between 30,000 and 50,000 Kelvin, far hotter than the Sun. Its colour would have been a brilliant blue-white, so intense that the ultraviolet radiation pouring from its surface would have ionized the surrounding gas for light years in every direction, creating a vast glowing bubble called an H2 region. The star would have been among the brightest objects in its neighbourhood, visible from enormous distances, a beacon of extreme energy. During this early phase, the star was on the main sequence, fusing hydrogen into helium in its core at a prodigious rate. A star 30 times the mass of the Sun burns through its hydrogen roughly 10,000 times faster than the Sun does. Not because it has 30 times more fuel, though it does, but because the core temperatures and pressures are so much higher that the fusion reactions proceed exponentially faster. The Sun has enough hydrogen to burn for 10 billion years. A star 30 times the mass of the Sun exhausts its hydrogen in just a few million years. The most massive stars we know of can run through their main sequence hydrogen supply in less than 2 million years. During the main sequence, the star was in a stable equilibrium. Gravity pulled inward, radiation pressure from the furiously burning core pushed outward. The star neither expanded nor contracted. It sat at a size of perhaps 5 to 15 solar radii, thousands of times smaller than its current bloated state. It was compact, hot, and stable. Then the hydrogen ran out. The core, now composed primarily of inert helium ash, could no longer sustain fusion at the rate needed to support the star's enormous mass. The core began to contract under its own gravity. As it contracted, it heated up, and the hydrogen in a shell surrounding the core ignited. This shell burning produced far more energy than the core had been producing during the main sequence. The excess energy flooded into the star's outer layers, causing them to expand. The star began to swell. Its surface cooled as it expanded, shifting from blue to white, to yellow, to orange to red. Over a period of perhaps tens of thousands of years, the star transformed from a compact blue giant into a vast red supergiant. Its radius grew from a handful of solar radii to hundreds, then past 1,000, approaching and possibly exceeding the theoretical limit. This transformation is not unique to Stephenson 2-18. Every star massive enough to become a red supergiant goes through this same process. What makes the most extreme cases special is the degree to which the expansion pushes the boundaries of stability. The outer layers of these stars are so far from the core, so loosely bound by gravity, so susceptible to radiation pressure, that they exist in a state of perpetual instability. The slightest perturbation, a change in the core burning rate, a convective eruption on the surface, a passage through a denser region of interstellar medium can cause the outer layers to shift, pulse, expand, or contract. This is why red supergiants are variable stars. Their brightness changes over time, sometimes regularly, sometimes irregularly. The variability is driven by pulsations in the outer envelope, driven in turn by the complex interplay between radiation pressure, convection, opacity changes as the gas heats and cools, and the overall structural dynamics of a star that is teetering on the edge of stability. Stephenson 2-18 specifically is classified as a variable star with strong silicate emission at infrared wavelengths, indicating a thick dust shell being continuously produced by the star's mass loss. Water masers have been detected in the circumstellar envelope, which are produced when water molecules in the envelope absorb energy from the star's radiation and re-emit it as intense focused beams of microwave radiation at specific frequencies. These maser emissions provide a way to study the dynamics of the mass loss process in detail, tracing the velocities and distributions of material as it streams away from the star. The mass loss itself is driven primarily by radiation pressure on dust grains in the outer atmosphere. In the coolest, outermost layers of a red supergiant's atmosphere, the temperature drops low enough for solid particles to condense out of the gas. Silicates, metal oxides, and other refractory compounds form tiny grains, each one perhaps a fraction of a micrometer across. These dust grains are very effective at absorbing and scattering the star's radiation. When a photon of light hits a dust grain, it transfers momentum to the grain, pushing it outward. The grain, in turn, drags the surrounding gas with it through friction. This mechanism, radiation pressure on dust grains coupled to the gas through friction, is the primary driver of mass loss in red supergiants. It is the reason these stars shed material so efficiently, and it is the reason their circumstellar envelopes are so dusty and so complex. The process is not steady or uniform. It varies with changes in the star's luminosity, surface temperature, and convective activity, producing the clumpy, asymmetric structures observed around stars like VY Canis Majoris and Stephenson 2-18. As the star loses mass, its gravity weakens. The outer layers, already loosely bound, become even less firmly attached. This creates a feedback loop. Mass loss reduces gravity, which makes it easier for radiation pressure to push more material outward, which reduces gravity further. The star is literally eroding itself from the outside in. At the same time, the core continues to evolve. After the hydrogen shell burning phase, the helium core becomes hot enough and dense enough to ignite helium fusion, converting helium into carbon and oxygen through the triple alpha process. When the helium in the core is exhausted, the core contracts again, heats up, and begins burning carbon. Each new fuel burns at a higher temperature, in a smaller region, for a shorter time. The timescales become extraordinary in their compression. If Stephenson 2-18 is currently in the carbon burning phase, it has perhaps 1,000 years left. If it has moved on to neon burning, it has about a year. Oxygen burning gives it months, silicon burning, days. In the final hours before core collapse, the star is burning silicon into iron at a temperature of several billion degrees in a core no larger than the Earth. The iron accumulates, inert, a dead weight at the center of the star. The core grows heavier. Gravity pulls harder. The electron degeneracy pressure that has been supporting the core against collapse reaches its limit. And then, in a fraction of a second, the core exceeds the Chandrasekhar mass limit of roughly 1.4 solar masses, the maximum mass that electron degeneracy pressure can support. The electrons are forced into the protons, creating neutrons and releasing a flood of neutrinos. The core collapses. The neutrinos are worth dwelling on because they represent one of the most remarkable aspects of stellar death, and because they might be our earliest warning if a nearby star is about to die. Neutrinos are subatomic particles with almost no mass and no electric charge. They interact with matter so weakly that a neutrino can pass through a light year of solid lead with only about a 50% chance of hitting an atom. trillions of neutrinos from the sun pass through your body every second without you ever knowing. They are, for almost all purposes, ghosts, but during the core collapse of a massive star, the number of neutrinos produced is so staggeringly large that even their feeble interactions become significant. In the final seconds of a supernova, the collapsing core releases roughly 3 × 10 to the 46 joules of energy, almost entirely as neutrinos. That is about 100 times more energy than the Sun will produce in its entire 10 billion year lifetime, released in roughly 10 seconds, almost entirely in the form of particles that pass through matter as if it were not there. We have detected supernova neutrinos exactly once in human history. On February 23, 1987, a blue supergiant in the Large Magellanic Cloud, roughly 168,000 light-years away, exploded as supernova 1987A. About 3 hours before the light from the explosion reached Earth, neutrino detectors in Japan and the United States detected a burst of roughly 25 neutrinos over a period of about 13 seconds. 25 neutrinos out of the roughly 10 to the 58 that the collapsing star had produced. The rest passed through the Earth without interacting. Those 25 neutrinos confirmed decades of theoretical predictions about how core collapse supernovae work. They provided the first direct observational evidence that the collapse releases most of its energy as neutrinos, not as light. And they demonstrated that neutrino detectors could serve as early warning systems for supernovae, since the neutrinos escape the star before the shockwave reaches the surface, meaning they arrive at Earth hours before the visible light. If Stephenson 218 were to undergo core collapse tomorrow, and if we had sufficiently sensitive neutrino detectors pointed in the right direction, we would detect the neutrino burst before we saw the star brighten or disappear. The neutrinos would arrive first, travelling at nearly the speed of light, carrying information about the collapsing core. A few hours later, the light would follow, either the brilliant flash of a supernova or the gradual dimming of a failed supernova as the star collapsed into a black hole. The current generation of neutrino detectors, including IceCube at the South Pole, Super Kamiokande in Japan, and the planned Hyper Kamiokande, are capable of detecting neutrino bursts from supernova throughout the Milky Way, an international network called the Supernova Early Warning System, or SNEWS, links these detectors together. If multiple detectors simultaneously register a burst of neutrinos with the right characteristics, SNEWS automatically alerts astronomers worldwide, giving them time to point their telescopes at the right part of the sky before the light arrives. We are, in a very real sense, waiting for the next galactic supernova. The last one visible from Earth was Kepler's supernova in 1604. We are overdue, statistically speaking. Somewhere in the Milky Way, a massive star is in the final stages of its life, its core growing heavier by the hour, approaching the moment of collapse. We do not know which star, we do not know when, but when it happens we will know. The neutrinos will tell us. Whether that star is Stephenson 2-18, or one of the other extreme red supergiants we have discussed tonight, or an entirely different star that has not caught our attention yet. The death of a massive star in our galaxy would be a once-in-a-generation event. It would be visible in the daytime sky. It would be studied by every telescope on Earth and in orbit. It would produce gravitational waves detectable by LIGO and Virgo. It would produce neutrinos detectable by IceCube and Super Kamiokande. It would be, in every sense, a scientific event of the highest order. Or if it is a failed supernova, it would be a disappearance, noticed only by the astronomers who happen to be monitoring that particular star, confirmed only by the absence of light where light used to be. A subtraction rather than an addition. The negative space left behind when one of the largest objects in the galaxy folds itself out of existence. Both outcomes tell us something. The explosion tells us about the physics of nuclear reactions, shockwave propagation, neutrino interactions, and the creation of elements heavier than iron. The disappearance tells us about the limits of those same physics, about what happens when the standard mechanism fails, about how black holes form in the real universe, rather than in the idealized models of our textbooks. Either way, the star teaches us something by dying. That is the nature of these extreme objects. They are laboratories. Their lives and deaths are experiments that the universe runs on our behalf, testing the laws of physics at scales and under conditions that we could never reproduce in any facility on Earth. Each observation we make, each measurement, each detection of a neutrino or a gravitational wave adds another piece to our understanding of how the cosmos works. The price of that understanding is patience. These events happen on their own timescales, indifferent to our curiosity. We cannot speed up the death of a star or schedule a supernova for a convenient observing window. We can only watch, wait, and be ready. And so we wait. Somewhere near the center of the galaxy, behind curtains of dust that block our view, the largest star we have ever found continues to burn. Its core grows heavier, its outer layers grow thinner. The dust shell surrounding it grows thicker and more complex. The mass emissions in its circumstellar envelope shift and change as new material is ejected and old material drifts away. Time passes. The star does not notice. Time is a human concept, a way of organizing our experience of change. The star does not experience time. It does not know it is dying. It does not know it is the largest of its kind ever observed by a species of primates on a small rocky planet 19,000 light-years away. It simply exists, following the laws of physics, converting mass into energy, shedding material into space, evolving toward its inevitable conclusion at whatever pace the physics dictates. For the star, there is no story. There is no beginning, middle, and end. There is only the continuous process of nuclear reactions and gravitational interactions playing out according to unchanging physical laws. The narrative arc, the sense of a journey from birth to death, is something we impose. We are the ones who see a pattern, a progression, a meaning. We are the ones who call it beautiful, or disturbing, or awe-inspiring. The star is just a star. But the fact that we can see the pattern, that we can trace the story, that we can calculate what the star was like when it was born, model what it is like now, and predict what it will be like when it dies, that is extraordinary. It means that the universe, for all its indifference, is at least knowable. Its processes can be understood. Its objects can be measured, even imperfectly. Its future can be predicted, even approximately. We are small, and the universe is large. We are temporary, and the universe is old. We are made of the debris of dead stars, and we will return to debris when we are done. But we understand what stars are. We understand how they live. We understand how they die. And that understanding connects us to every star that has ever burned, every atom that has ever been forged in a stellar core, every photon that has ever crossed the void between the stars, including the photons leaving Stephenson 218 right now, travelling at the speed of light across 19,000 light-years, of dusty, empty, silent space, carrying information about a star that is too large to exist, too unstable to last, too far away to visit, and too hidden to see. Those photons will arrive at Earth roughly 19,000 years from now. Whoever is here to detect them, if anyone is here at all, will be looking at the star as it is tonight. They will see the same red glow, the same dusty envelope, the same massive structure teetering on the edge of the Hayashi limit. They will wonder, as we wonder now, whether the star has already died, its death light still in transit, or whether it still burns. And perhaps they will know the answer. Perhaps by then, better instruments and deeper understanding will have resolved the questions we cannot resolve tonight. Perhaps they will know the star's distance precisely. Perhaps they will know its radius to within a few solar radii. Perhaps they will know whether it exploded or collapsed and what it left behind. Or perhaps the questions will still be open. Perhaps the universe will still be keeping its secrets, offering glimpses but not certainties, measurements but not precision, understanding but not completeness. Either way, the star or the remnant of what was once a star will still be there. A part of the galaxy, a contributor to the cosmic cycle of matter and energy. A chapter in the long, unfinished story of a universe that is still making itself up as it goes along. That is where we'll leave it tonight. Not with a conclusion, because there is no conclusion yet. The story of the biggest star ever discovered is still being written, in photons and neutrinos and gravitational waves, in journal articles and telescope observations, in datasets and computer simulations. It will continue to be written long after tonight is over. For now, the star burns, the dust drifts, the photons travel, the universe continues. And you, made of atoms forged in stars not unlike this one, are here, listening, in the dark, thinking about a light you cannot see, from a star that should not exist, that will someday either explode or disappear. But the story does not end with the star's death, because long before it reaches that final moment, it has already been doing something remarkable. Long before Stephenson 218 reaches its final moment, whether that moment is an explosion or a silent collapse, it has already been seeding the universe with the raw materials for everything that will come after. Red supergiants are element factories. During their main sequence lives, they fused hydrogen into helium. As they evolved, they fused helium into carbon and oxygen, carbon into neon and magnesium, and so on up the periodic table. These heavier elements, forged in the crushing pressures and temperatures of the stellar core, are gradually mixed outward through convection, dredged up from the depths and brought to the surface layers. And then the mass loss takes over. The enormous stellar winds that strip material from the surface of a red supergiant carry these elements into interstellar space. Carbon, oxygen, silicon, magnesium, iron, all the building blocks of rocky planets, of water, of organic chemistry, are blown off the star's surface and dispersed into the surrounding interstellar medium. Over the course of its red supergiant phase, a star like Stephenson 2-18 may return several solar masses worth of enriched material to the galaxy, material that will eventually be incorporated into new molecular clouds, new star-forming regions, new solar systems. If the star dies in a supernova, the explosion adds even more. The tremendous temperatures and neutron fluxes during the supernova itself create elements heavier than iron. Elements like gold, platinum, uranium, elements that cannot be created by any other process in the normal lives of stars. These elements are scattered into space by the expanding supernova remnant, mixing with the surrounding gas, enriching it. If the star dies in a failed supernova, if it collapses silently into a black hole, then this supernova enrichment does not happen. The elements trapped in the star's core fall into the black hole and are lost. But the material already shed by the stellar wind during the red supergiant phase is still out there, still drifting through space, still available to be swept up by the next generation of star formation. This is the cycle. Massive stars are born from clouds of gas. They burn for millions of years. They forge heavy elements in their cores. They shed those elements into space through stellar winds, and if they explode, through supernova ejecta. The enriched material mixes with the interstellar medium. Eventually, gravity pulls it together into new clouds. Those clouds collapse and form new stars, surrounded by disks of gas and dust from which planets form. The planets contain the heavy elements created by the previous generation of stars. And on some of those planets, those heavy elements assemble into molecules, then into complex chemistry, and then rarely into life. The calcium in your bones was created in a star. The iron in your blood was forged in a stellar core. The oxygen you are breathing right now was produced by nuclear fusion inside a massive star that lived and died long before our sun was born. The carbon in every organic molecule in your body, every protein, every strand of DNA was cooked inside a star and delivered to the interstellar medium through exactly the same process that is happening in Stephenson 218 right now. You are quite literally made of stellar debris. And not just any stellar debris. You are made of debris from stars that were massive enough to produce heavy elements, stars in the same general category as the ones we have been discussing tonight. Stars that lived fast, burned hot, swelled to enormous sizes, and then died, scattering their processed material across the galaxy for the next generation to use. This is not a metaphor. This is nuclear physics. The atoms in your body carry signatures of the nuclear reactions that created them, specific isotope ratios that tell you which process forged them, which type of star, what temperature, what pressure. When a geochemist analyzes a meteorite and identifies isotopic anomalies, they are reading the fingerprints of ancient dead stars. When an astronomer measures the spectral lines in a distant star and determines its chemical composition, they are looking at the recycled output of stars that died before that star was born. The larger stars play an outsized role in this cosmic recycling. Not because they are the most common, they are not. Red supergiants are rare. Stars massive enough to become red supergiants make up only a small fraction of all stars born. Most stars are small, cool red dwarfs that will burn for trillions of years without producing any significant heavy elements. The massive stars are the outliers, the exceptions, the rare ones that burn hot and bright and die young. But their contribution is disproportionate. A single massive star can produce and distribute more heavy elements in its few million years of life than 1,000 red dwarfs will produce in 1 trillion years combined. The rare, extreme, short-lived stars are the ones that enrich the galaxy. Without them, the universe would contain only hydrogen and helium, the two simplest elements, the only ones created in the Big Bang. No carbon, no oxygen, no silicon, no iron, no rocky planets, no water, no chemistry, no biology, no life. The stars that are too big to exist, the ones that push the Hayashi limit and challenge our models, are the very stars that made our existence possible. There is a quiet irony in this. The largest star we have ever found is dying. It is in its final evolutionary phase, probably with only a few 100,000 years of life remaining, possibly much less. It is tearing itself apart, shedding its outer layers into space in great gusts of dust and gas. By any standard, it is a star in crisis, unstable, oversized, running on borrowed time. And yet the material it is shedding will outlast the star itself by billions of years. The atoms it is distributing into the interstellar medium right now will eventually be pulled into new star-forming regions, compressed into new solar systems, incorporated into new planets. Some of those atoms may end up in the atmospheres of new worlds, some may end up in oceans, some, through the long, improbable chain of chemistry and biology, may end up in living things. The largest star we have ever found will die, that is certain, but what it leaves behind will persist, recycled and reused across generations of stars, for as long as the galaxy endures. Let us now step even further back and consider what Stephenson 2-18 looks like in the context of the galaxy as a whole. The Milky Way is roughly 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars. The uncertainty in that number is large because we are inside the galaxy trying to count stars while embedded within the structure, surrounded by dust and gas that blocks our view in many directions. Some stars are hidden, some are too faint to detect, some are in regions we simply cannot observe from our position. Stephenson 2-18 sits roughly 19,000 light-years from Earth, in the direction of the constellation Scutum, near the dense star fields of the inner galaxy. It is not visible to the naked eye. It is not visible through a modest telescope. It is hidden behind thick dust lanes that block visible light and can only be observed in the infrared. If you were to point a backyard telescope at the patch of sky where Stephenson 218 sits, you would see nothing but stars and dust. The largest star we have ever found is invisible to your eyes. This is worth pausing on. The largest known structure in the category of individual stars, an object with a volume 10 billion times that of the Sun, an object whose surface would swallow Saturn if placed at the centre of our solar system, is invisible without specialised instruments. It is a speck in the galaxy, an unremarkable point among hundreds of billions of stars. If you were looking at the Milky Way from outside, from a vantage point in intergalactic space, millions of light years away, you could not find Stephenson 2-18. You could not distinguish it from its neighbours. It would be lost in the glow. The galaxy does not care about the size of an individual star. At galactic scales, even the most extreme stars are negligible. The Milky Way is shaped by the collective gravity of hundreds of billions of stars, by the vast dark matter halo that contains roughly 10 times as much mass as all the visible matter combined, by the supermassive black hole at the centre, Sagittarius A star, which weighs about 4 million times the mass of the Sun. A single red supergiant, even the largest one, contributes almost nothing to the total gravitational budget of the galaxy. And the Milky Way itself is just one galaxy among an estimated 2 trillion in the observable universe. 2 trillion galaxies, each containing hundreds of billions of stars, spread across a volume 93 billion light-years in diameter. The observable universe contains roughly 200 billion trillion stars. That is, a 2 followed by 23 zeros. Stephenson 2-18 is one of them. From this perspective, the largest star ever found is almost indescribably insignificant. It is one object among 200 billion trillion. Its impressive size, so far beyond anything our intuition can process, is rendered meaningless by the sheer number of other objects surrounding it. The universe does not have a sense of scale that matches ours. Things we find impossibly large are routine in the cosmos. Things we find incomprehensibly rare, like stars exceeding the Hayashi limit, are probably happening right now in galaxies we will never observe. And here is the final layer of the disturbing truth. We call Stephenson 2-18 the largest star ever discovered, but that phrasing is misleading. It is the largest star ever discovered by us. There is no reason to think it is the largest star that currently exists. Our observations cover only a fraction of our own galaxy, and that fraction is heavily biased towards certain types of stars in certain directions at certain distances. We cannot see through the galactic centre. We cannot see to the far side of the Milky Way. We cannot see through the densest dust clouds. We cannot detect every faint, cool, dust-enshrouded red supergiant lurking in the spiral arms. In the Large Magellanic Cloud, the Small Magellanic Cloud, in the Andromeda Galaxy, in the Triangulum Galaxy, in the thousands of galaxies within 100 million light-years of us, there are untold numbers of red supergiants we have never observed and cannot currently measure. Some of them may be larger than Stephenson 2-18. Some of them may be considerably larger if the Hayashi limit is not exactly where we think it is. And beyond the observable universe, in the vast expanses of space that light from the Big Bang has not yet had time to reach, in regions of the cosmos that we will never be able to observe, no matter how advanced our technology becomes, there may be stars whose sizes would dwarf even the most extreme objects in our catalogues. We have no way of knowing. The universe is under no obligation to place its most impressive creations within our field of view. The title of largest star is a temporary designation. It will change. It has changed multiple times in the past as measurement techniques have improved and new surveys have revealed previously unknown objects. VY Canis Majoris held the popular crown for years. Then UY Scuti took it until its distance was revised. Now Stephenson 2-18 holds it uncertainly, with caveats and error bars, and the ever-present possibility that a more accurate measurement will reduce its estimated size significantly. And at any time, a new survey, a new infrared observation, a new interferometric measurement could reveal another star, slightly larger, slightly farther away, pushing the record incrementally higher. The record does not matter. What matters is what these stars tell us about the physics of the universe. They tell us that stellar evolution models work extraordinarily well for the vast majority of stars, but break down at the extremes. They tell us that measurement is not certainty, that distance errors propagate into size errors, that the boundary of a star is not a clean line, but a gradual fade. They tell us that some stars die in spectacular explosions and others die in silence, and we cannot always predict which will happen. They tell us that the elements in our bodies were created in stars like these, and that the cycle of stellar birth, life, death, and rebirth is the engine that drives the chemical evolution of the galaxy. And they tell us something about the limits of knowledge itself, that there are objects in the universe we can detect but not fully understand, that our best instruments are reaching toward the edge of what they can resolve, and our best theories are reaching toward the edge of what they can predict. That the honest answer to the question, how big is the biggest star, is we think we know, but we are not sure. And that uncertainty is itself a form of knowledge. Tonight, roughly 19,000 light years from where you are lying right now, in the direction of the constellation Scutum, behind thick curtains of interstellar dust that block all visible light, a star burns. It is red, it is cool by stellar standards, roughly 3,200 degrees Kelvin, about 5,300 degrees Fahrenheit. Its surface, such as it is, glows a deep ember red, the colour of a dying coal. The light it produces is dominated by the infrared, invisible to human eyes. It is enormous. Its radius stretches roughly 1.5 billion kilometres outward from its centre, a sphere so vast that it takes light nearly 9 hours to trace a single circle around its equator. If it sat where the sun sits, it would fill the solar system out past Saturn. Jupiter and all the inner planets would exist within its diffuse, superheated outer atmosphere. It is losing mass. Great plumes and arcs of gas and dust are being driven off its surface by the relentless outward push of radiation pressure. These plumes extend for hundreds of billions of miles, slowly drifting into the interstellar medium, carrying with them the carbon, oxygen, silicon, and other heavy elements cooked in the star's core over millions of years. This material will eventually be swept up by new star-forming regions, compressed into new solar systems, incorporated into new worlds. It is dying. The core is burning through its remaining nuclear fuel at a rate that accelerates with each successive stage. The hydrogen is long gone. The helium is depleted. Carbon, neon, oxygen, silicon, each fuel ignites and is consumed in progressively shorter periods. The core is contracting, heating, approaching the moment when iron accumulates, and fusion can go no further. When that moment comes, the star will reach its end. It might explode in a supernova visible from Earth, a new star appearing in the sky near the centre of the Milky Way, bright enough to see in daylight for weeks, a once-in-a-civilization event. It might collapse directly into a black hole, the star's immense bulk folding in on itself without a sound, the light simply going out, a cosmic vanishing act. It might produce a hypernova, one of the most energetic events in the universe, accompanied by twin jets of relativistic plasma and a burst of gamma radiation detectable from across the cosmos. We do not know which ending awaits. We may never know until it happens. And it may have already happened 19,000 years ago, the light from the event still racing toward us through the dust and the void, carrying the news of a star's death that we will not receive for millennia. In the meantime, the star burns. It burns in a part of the galaxy we cannot see with our eyes. It burns behind walls of dust that render it invisible in the wavelengths we evolved to perceive. It burns at temperatures too cool for our eyes to see, even if we could look at it directly. It is, by nearly every measure of human perception, completely invisible and utterly unnoticeable, and yet it is the largest star we have ever found. There is something in that juxtaposition that feels important. The most extreme object in our stellar catalogue is hidden from us. The most extraordinary example of what physics can produce is invisible to our natural senses. We did not find it by looking. We found it by building instruments that could see what our eyes could not, by developing mathematical models that could interpret what those instruments detected, by layering inference upon inference until a picture emerged of something impossibly, disturbingly large. This is what science does. It extends our senses into domains our biology never equipped us to perceive. It reveals structures and processes that exist far beyond the narrow band of experience our bodies can access. The infrared universe, the radio universe, the X-ray universe, the gravitational wave universe, none of these are visible to human eyes. All of them are teeming with phenomena that are as real and as consequential as anything we can see or touch, and all of them were invisible to us until we built the tools to perceive them. Stephenson 218 is one of those invisible revelations, a star we could never have known about without infrared telescopes, interferometry, spectroscopy, and mathematical modelling. A star whose very existence challenges the boundaries of what our physics says is possible. A star that will die one way or another, in an event we will either witness as a light in the sky or miss entirely as a silent disappearance. A star that, for all its incomprehensible size, is just one among 200 billion trillion stars in the observable universe. That is the disturbing truth about the biggest star ever discovered. Not just that it is large, though it is. Not just that it is dying, though it is. Not just that it might not even be as big as we think, though that is true too. The disturbing truth is that it exists at the boundary of what we can know, where our measurements become uncertain, our theories become approximate, and the universe resists our attempts to pin it down with clean, definitive numbers. The biggest star ever discovered is not a fact. It is a best estimate, wrapped in uncertainty, standing at the edge of our instrument's reach and our physics' ability to explain. And somewhere beyond it, hidden in dust we cannot penetrate, at distances we cannot accurately measure, in wavelengths we may not yet have the technology to observe, there are almost certainly stars, even larger, stars we have not yet found, stars we may never find. The universe is vast beyond our ability to fully catalogue, full of objects beyond our ability to fully measure, governed by physics beyond our ability to fully predict. And yet here we are, a species on one small planet, orbiting one average star in one ordinary galaxy, lying in the dark, trying to understand a star 19,000 light years away that is 2,150 times the size of our Sun. And we are getting closer to understanding it, piece by uncertain piece. That effort, that reach toward understanding, is itself a kind of defiance against the scale of the cosmos. We are small. The universe is not built for us. The distances are too large, the timescales too long, the objects too extreme for our brains to comfortably process, but we process them anyway. We build telescopes, we write equations, we debate measurements, we refine theories, we sit with uncertainty and call it progress. We will not be here when Stephenson 218 dies. Whatever form that death takes, whether it lights up the sky or disappears in silence, it will happen long after every person listening to these words tonight has returned to the elements that formed them. The calcium in your bones will be in the soil, the iron in your blood will be in the earth, and the atoms that made you, forged in ancient stars not unlike the one we have spent tonight discussing, will be available to the universe for whatever comes next. That is the cycle. Stars are born, stars die, the material is recycled. New stars form,